Way ANOVA. Suppose a medical researcher is analyzing the effectiveness of 3 types of pain relievers and wants to determine if there is a difference in the mean length of time it takes the 3 medications to provide relief. To determine whether such a difference exists, the researcher can use something that we call F distribution, together with a technique that we call analysis of variance, or ANOVA. Because one independent variable is being studied, the process is called one-way analysis of variance. Definition: one-way analysis of variance is a hypothesis testing technique that is used to compare the means of 3 or more populations. Analysis of variance is usually abbreviated as ANOVA. To begin a one-way analysis of variance test, you should first state the null and alternative hypothesis. For a one-way ANOVA test, the null and alternative hypotheses are always similar to these statements. So it makes it a little bit easier for us. The null hypothesis says, well, the population means are all the same. Its opposite, at least one mean is different from the other ones. When you reject the null hypothesis in a one-way ANOVA test, you can conclude that at least one of the means is different from the others. Without performing more statistical tests, however, you cannot determine which of the means is different. Before performing a one-way ANOVA test, you must check that these conditions are satisfied. First, each sample must be randomly selected from a normal or approximately normal population. 2, the samples must be independent from each other. And 3, each population must have the same variance. The test statistic for one-way ANOVA test is the ratio. It's a fraction of 2 variances: the variance between samples and the variance within samples. So your test statistic that requires a lot of calculations is a fraction. On the numerator of your fraction, you have the variance between samples, and on the denominator, you have the variance within samples. The variance between samples measures the difference related to the treatment given to each sample. This variance, sometimes called the mean square between, it's abbreviated by MS sub B. The variance within samples measure the differences related to the entire entries within the same sample and is usually due to sampling error. The variance called the mean square within, and it is abbreviated as MSW. Very good. So when it comes to one-way analysis of variance, you have the following steps. To perform a one-way ANOVA test, these conditions must meet. Each of the K samples, K must be more than or equals to 3, must be randomly selected from a normal or approximately normal population. 2, the samples must be independent. 3, each population must have the same variance. If these conditions are met, then the sampling distribution for the test is approximated by F distribution, and you can move on to calculate the test statistic. The test statistic F is MSB divided by MSW. The degrees of freedom for the numerator is degrees of freedom n for the numerator, which is k minus 1. What is k? K is the number of samples. And for your denominator, you're going to use a different degrees of freedom. The degrees of freedom for the denominator is n minus k, and n is the sum of the sample sizes. In more detailed steps, let's follow the guidelines. Finding the test statistic for a one-way ANOVA test. First, find the mean and variance of each sample. The mean of each sample is denoted by x bar. The variance of each sample is denoted by s squared. Find the mean of all entries, which is also called the grand mean. It has 2 bars on top of it. X with 2 bars is the grand mean. It's the summation of all x values divided by n. Then find the sum of squares between the samples. The sum of the squares between the samples is the summation of ni's times the difference between each sample average and the grand average squared. 4. Find the sum of the squares within the samples. Sum of squares within, which is the summation of the difference between ni and 1 times the variance. Find the variance between the samples, MSB, which is basically the sum of the squares between samples divided by the degrees of freedom for the numerator. Mathematically, it's the summation of ni's times the difference between each sample mean and the grand mean to the second divided by k minus 1. 6. Find a variance within the samples, which is MSW equals to sum of the squares within the samples divided by degrees of freedom of the denominator. Mathematically, it is the summation of ni's minus 1 times the variance divided by n minus k. And then find the test statistic, which is the division between MSB and MSW. And then in performing the hypothesis testing, make sure the samples are random, independent, the population is normal or almost normal, and variances are equal to each other. Identify the null alternative hypothesis, H sub 0, H sub A. Specify the level of significance, alpha. And as usual, if it's not given, by default, it is 5%. Determine the degrees of freedom for the numerator and the denominator. The degrees of freedom for the numerator is k minus 1. The degrees of freedom for the denominator is n minus k. Determine the critical value using the table. And determine the rejection region, everybody. If the test statistic is inside the rejection region, you're going to reject the null hypothesis. Otherwise, you're going to say that, hey, we failed to reject the null hypothesis. So let's go back to the medical researcher. A medical researcher wants to determine if there is a difference in the mean length of time it takes 3 types of pain relievers to provide relief from headache pain. So that researcher is going to select random people who suffer headache and give one of the 3 medications to each. Each headache sufferer records the time in minutes it takes the medication to work. The results are shown in the table here. For the first medication, the first person took 12 minutes to relieve the pain, the second person 15 minutes, the third person 17 minutes, the fourth person 12 minutes, and as you can see, you have n sub 1, which is 4. You have 4 people in the first medication category. If you find the mean of the first medication category, it is 14 minutes average with variance 6. Second medication category, the first person reported 16 minutes, the second person reported 14 minutes, the third person reported 21 minutes after taking the medication, the headache starts to reduce. The next person 15 minutes, then 19 minutes, and you have 5 people in this category. The average time that takes for the second medication to work is 17 minutes with variance 8.5 minutes. The third medication category, you only have 4 people, 14 minutes, 17 minutes, 20 minutes, 15 minutes. The average time that it took for the third medication to start working is 16.5 minutes with variance 7 minutes. Very good. So the null and alternative hypotheses are as follows. Null hypothesis says, hey, the mean time for all of these population for these categories are the same. Its alternative hypothesis, at least one mean is different from the others, and this is your claim. Because there are k equals to 3 samples, degrees of freedom of the numerator is k minus 1 or 2. The sum of the sample sizes is n equals to n1 plus n2 plus n3, which is 4, plus 5 plus 4, which is 13. So the degrees of freedom for the denominator, which is n minus k, is 13 minus 3, or 10. Using the degrees of freedom for the numerator 2 and the degrees of freedom for the denominator 10 and alpha equals to 1%, the critical value for your F distribution is 7.56. 7.56. So this is a regular F distribution. Here you have for 5%, F distribution for 2%, F distribution for 1%. This is the degrees of freedom for the denominator, and this is for 1% level of significance. So F distribution has different tables based on the numerator, based on the denominator, and using different level of significance. So let's go back to our example. The rejection region is for any value that is more than 7.56. To find a test statistic, first we need to calculate the grand mean, which is the summation of all x values over n, 56 plus 85 plus 66 divided by 13, or about 15.92. Now, the mean square of the sample betweens, which follows the summation of ni's, xi bar, minus the grand mean to the second divided by k minus 1. Well, we have a lot of calculations to do. Based on our table, the very first n for sample size is 4. The mean of the first sample is 14, minus the grand mean that we calculated here, 15.92. Raise it to the second power plus 5 times the mean of the second category, 17, minus 15.92. Raised to the second power plus 4, the number of data in the third category, times the average of the third category minus the grand mean to the second divided by k minus 1, which is 2. If you do the division, for now we have 10.9616. Now let us calculate MS of within. We need to add ni's minus 1 times their variance and then divided by n minus k. The very first n is 4 minus 1 times the very first variance, which is 6, plus n minus 1 for the second sample is 5 times its variance, which is 8.5, plus 4 minus 1, which is the number of data in the last category, minus 1 times the variance, which is 7 divided by 13 minus 3, 73 divided by 10, which is 7.3. So with these pieces of information, we can basically calculate F, which is our test statistic. Is test statistic inside the rejection region? Definitely not. Why? Because our critical value is 7.56, which lands here, and the rejection region is on the right-hand side. But the test statistic is outside the rejection region. So we do not reject the null hypothesis. Because F is not in the rejection region, you fail to reject the null hypothesis. It means that you support the null hypothesis. There is not enough evidence at 1% level of significance to conclude that there is a difference in the mean length of time it takes the 3 pain relievers to provide relief from headache pain. The ANOVA summary table can be written this way as well. You have the variation, the sum of squares, in between, within, degrees of freedom, and the mean squares, and finally calculating F, which is your test statistic. Then check to see if test statistic is inside the rejection region or outside the rejection region. And again, the table that we're using is just right here. The degrees of freedom for the numerator. So if you go back and take a look at the degrees of freedom of the numerator, it is 2, and the denominator, it is 10. So here we have a 2, and here we have a 10. So as you can see, 7.56 is indeed the critical value that you're using for 1% level of significance. 2 and 10, they have an intersection, 7.56.